tools of ordinal correlation coefficients, Spearman correlation, for instance. So do we really need the CCCs?
So the CCC is based on rank, and ranks cannot go very bad. Like the centrality measures might become really bad. Like so, like kind of you need moment bounds for centralities for Spearman coefficients. Are they based on ranks? I actually don't recall.
Yeah, they're also based.
They are
on
based
ranks.
on ranks.
Yeah, yeah.
But so I have to think about this question. But there are other properties which are also interesting in this. Probably like they do not the other measure do not hold that. So you can talk about the convergence of these kind of curves. It's like you can have a solid theory about it. So which I talk about in the later sections, and you can prove some results which are probably not. I have to read about the Spearman's coefficients results, but so these results are like doable for the sparse regimes graphs which are locally converging. You can talk about the CCC being convergent to some very nice deterministic curve for a certain class of centrality measures under some assumptions which are true for certain class of centrality measures. So probably that's what makes it more interesting. But yeah, but I have to think about it.
I think actually building on what you're now saying, I think you might perhaps make the argument that your CCC approach potentially, although I think you don't really demonstrate that in the thesis, but potentially it might actually offer an alternative to these traditional correlation coefficients like Spearman, an alternative that has certain benefits that these traditional correlation coefficients don't have. And potentially benefits that actually are of use, not only in the context of networks, but in much broader contexts in which correlation measures are used. So this is for me a bit of a puzzle that in my mind is still there when I read this part of your thesis about the CCC measures. If there's still time, I would like to briefly conclude by asking one more question, and that is about the bigger picture that emerges from your work. So I'm in a field of research where people use lots of centrality measures, but these researchers that use these measures are doing this in a much more applied way. They don't study all these mathematical properties that you study, for instance. And to be honest, I think the literature in my field is quite messy. People use all kinds of centrality measures without really understanding what they are doing. So I was wondering, how do you think your work might actually help creating more rigor in the more applied research fields, for instance, in the social sciences, where all these centrality measures are being used? Because I believe there's a strong need for that. Do you have any thoughts on this?
I have to think about that. It's a very hard question. So I am a very small drop in the ocean of people who are doing research, but I think like people, if like little by little, that might be little bit changes. But I have tried my bit to little bit make it more organized and try to tell about these centralities. So you need more people to think about these problems, and if more people think about these problems, it will become so kind of even defending right now. My people might be listening to this and getting interested in this problem. That is also one of the things that's part of it probably. Like all the people collectively think about problems and try to like put their minds into it. That's a philosophical answer. I'm sorry about
Thank you for your answers.
Thank you very much, Professor Waldman. Let's just check with the secretary. Is the connection reestablished?
Yeah, we don't know that. We have to check that. So the audio video team suggests to give the word to Professor Atreya again and at least try. So hopefully it will work this time.
Okay, let's try. Professor Atreya, can you try?
Yes, can you hear me now?
Just give a second, we have to test, because I think it's better than to join the meeting. So shall I invite it, or at least go ask them what is happening now?
Yeah, ask some technical assistance. Okay, in the meantime, we can continue with Professor Exarchakos.
Yeah, thank you, Mr. Chairman. Geachte promovendus, I read with a lot of interest your thesis. Of course, we have had a lot of discussions before, but reading it through is quite important and useful. I do have a lot of questions regarding I think the vertex removal process. Let's start from that. You concluded in that chapter about the quality that the process is relying on the quality of the measures, the quality of importance of the measures. Now, first question was, is there only a single quality that we measure in any type of network, or there can be multiple qualities?
Ziglade, dear promoter, thank you for your kind words and nice questions, nicely phrased questions. So the question was regarding that, is this the only method of like qualitatively comparing? The answer is no. But this kind of this method tells you the how like these which vertices preserve the structure much better. So you can compare centrality measures in a different way, but in this method you are talking about this structural property of the networks, and yeah, there might be different methods how you can compare. That's how I would conclude my answer. Yeah.
Okay, I would like to follow up on this. So let's assume that we have multiple qualities of importance, so for different regions. Is it realistic to say that there can be a mapping of one network to a different network, like transformation of a graph to a different graph, where we can apply your method but conclude on qualities that are not tested directly by the tested by that process? Is it possible to have a generic method, use your method as a generic process to detect multiple qualities on a graph by transforming the graph
That might
itself?
be possible for a small class of comparison techniques, but I don't think for a generic class, because like there might be some like this kind of so the problem of comparison of centralities is context dependent. So if you are after the structure of the network, if you want to find structurally strong vertices which structurally preserve the size of the network, the connectivity properties of the network, then and some kind of measures which are a little bit related to this, then you can probably transform or something like that. But if the centrality, if the comparison is like something totally different in a different context, I cannot think of an example, but something like probably you don't want to destroy the structure, you want to preserve the structure, something like that. That's in that way, if you want to compare, then probably or something totally different, then you might not be able to transform and get it from this comparison technique.
Okay. Okay, thank you for your answer. I would like to move to the comparison curve. And then in that curve, then we saw that you have detected a number of properties. So first of all, I was wondering, do we know there are no more properties? Just as an example, if we compare A and B, and then B and C centralities, can we argue something about A to C?
Probably, I feel like so there are examples. Probably, maybe I can find a counterexample related to this. But mostly, I think if so, in similarity there is clustering of centrality measure. I feel like that with the few examples I had simulated. So I felt like, but obviously it's not proven. So it's not, I have not proven this, or anyone has not looked at it theoretically. But I think that similar centrality measures cluster, but obviously there might be some counterexamples for this. But mostly that might be true.
Thank you. Mr. Chairman, should I continue or this time?
Continue.
Yeah, okay. Thank you very much. Okay, so how sensitive is the comparison curve to small or big differences in between the measures of different centralities? Because you're comparing, so like if there is a small difference, what does it mean to the curve? Is it
So these are like, as its first property was monotonically increasing function. If you use any monotonic increasing function, like translation or multiplication by a constant, a positive constant, this is invariant.
okay?
So maybe I'm not getting the question right, but changing a little bit of the centrality measures, like both centrality measures, that won't change the ranking that much, and
Okay.
indirectly the centrality comparison curve will also not be the change that much. But if you're talking about just changing the one centrality measure by a bit, that might create problems.
Do we know if there's
But because of the tie-breaking rule, so we have a tie-breaking rule which introduces uniform random variables at each node, and so that kind of makes the centrality comparison curve continuous in some sense. So little alterations might not affect that much, but you have to sit with a pen and paper to prove this. But yeah, that is my response to that question.
Okay. Thank you for your answer. I would move to the use cases, to the applications that you detailed in your thesis, and especially the OLFAR, the orbiting low frequency array. To your perspective, after pruning and choosing the K for keeping the network connected, the KNN network connected, there can be, even after doing that, there can be multiple paths from any vertex to any other vertex, right? Do you think that the removal process that you described, or the comparison curve, can be used to pick the best path between these two vertices, or any other way that you would think these two methods would be useful for that use case?
I don't think so, because like this problem of finding paths, although there might be some very complicated way of like catching your ear from the this hand, this side, like, but I cannot see something which like you can use these methods. These methods are like useful to compare centralities. Probably you can know which satellites you can rely upon for the structural integrity of the satellite network. But knowing, yeah, I don't think so. But yeah, I might be wrong. I don't know.
But so isn't it important to keep the network connected? And even if we detected the amount of the size of the neighborhood K, wouldn't we still want to rely on nodes that are more important?
Yeah, that is true. So the first method might tell you about which satellites preserve the structural integrity of the networks. So you know exactly which satellites like are really like can destroy the network, but there might be some satellites which malfunctioning of those satellites might not affect the network as much. Yeah, but these are interesting questions.
Okay. Do I have time? Mr. Chairman, do we have time for one more?
One small question.
One small question, maybe a challenging one. I look at your slide and I see a clear question there. Who is the most influential in a network?
Yeah.
So I'm begging for an answer.
So it is context dependent. For me, my family is the most important in my network. Yeah. Yeah.
Okay.
Yeah. Yeah.
Okay. Thank you very much.
Thank you very much, Professor Exarchakos. Shall we try to establish the connection to Bangalore? Professor Atraya, are you there?
I am still here. Can you hear me now?
Very good, very good. Good to hear. Welcome to Eindhoven. Please continue the opposition.
Dear candidate, I'm hearing a small echo, but it's okay. I enjoy reading the thesis, the eight chapters, and very well thought out. I'll just begin with a very generic question. In your thesis, what would you characterize as your most impactful or your most liked result?
Okay. Dear opponent, Professor Atreya, thank you for your kind words and the nice question, nicely phrased question. So for me, I am a little bit, I think I feel like the chapter 6 and the chapter 4. So the sixth chapter is about cascading dynamics in networks. And the fourth chapter is about the centrality comparison curves and the basically there are some results which I prove, which we prove, like with all the my supervisor and everyone. So which I feel like were the most challenging months. Like when I and I feel like those results are like more impactful for me at least, but obviously I'm a drop in the ocean, and as I already said, but yeah, that's my take on that. Yeah.
Okay, so then I had a couple of generic questions to ask on the technique. So you have discussed in great detail this vertex removal procedure.
Right.
And also I'm very appreciative of the fact that centrality measures have been around for quite some time, and you have taken a step to make things. So I just want to understand: are there centrality measures available that are more amenable to, let's say, a motif removal of some kind, like a wedge or a triangle? Do you have any ideas on that?
So that's a very yeah, let me think. So that's a very interesting question. I have never thought about this question like that, but probably like you can look at it in that way. So removing which vertices might remove these kind of motifs which we are targeting from the network, like a triangle. If you want to make a triangle-free graph, and which vertices should you attack? That's a very interesting question to think about. But thinking it on the spot is very difficult, probably. But I'll think about it probably later on. Yeah. I'm sorry.
No problems. So let me go to an application question, and then I will come back to this technical side again. So just the previous question was on how to identify an influencer. That's one question, or who will be an influencer in the network. Is there a way to use centrality to understand how to control the influence of the influencer?
Influence of the influencer. Okay.
Right. How do you measure that, or how do you control it? Do you have any idea? Because that's a very keen application problem these days in terms of networks.
So if you look at like very intuitively, then probably people might think that popularity is just like influencing. You have more followers, you can influence more, but actually it's a little bit more complicated. In a network, the word spreads like from one person to the other person, and from the other person to the third person, so on. So probably just not looking at the locally, but looking a little bit more further, like what is done in eigenvector centralities. You are looking at the influence of the people you are influencing, and kind of you are looking at the sum of these, the average of basically these. The recursion is based on that, the fact that if you are influenced, if the people you are influencing, if they are more influential, then you are even more influential. So this recursion gives you something called eigenvector centrality, and there are many other examples of this. But like these kind of measures are present in the literature. Is that what you were looking for or
No, it's okay, but I just want to understand: are there ways to control the influences?
controlling?
Are there,
Control.
yeah.
Okay.
Okay, that's okay. We can think about it. So I'll go back to the technical side again a little bit. Can you explain in a little detail in general terms? There's very interesting way you model cascades. Like, what's the technical challenge there, and how did you resolve it?
Okay. So the technical challenge is about the uniqueness of the cascade surviving cores. So the very common example that many people might know is about the K core. So let's just talk about cascade surviving core. So what does the cascade surviving core does is that you look at the most. So you look at any property, like that property can be if you have more than K neighbors. So if you remove the vertices which have more than K neighbors, keep doing it until you have all the people having more than K neighbors. So either you get a like empty graph, or you get a highly connected core structure. So in like some properties like degree, you had already shown that this is unique. You get like it doesn't depend on the order in which you are removing the vertices. But for the cascade surviving core, we use general properties, and we prove that like for a certain class of properties, like the monotonically increasing properties, which we call, you have the unique cascade surviving core. After that, you have a proper definition, then you can start studying about these properties in detail, talk about the core. This was the technical challenge probably. And later on, like obviously the proof was also a challenge, but just defining it first was the first challenge in the step.
Okay, I'll close with one last question, and then I think my time is almost up. In terms of applications, let's go again. So do you really believe in one of the open problems you say that you'll be able to address sort of dynamic power sharing and satellite communication? Is that a realistic belief, or is it sort of you think that's nearby in terms of mathematical rigorousness?
Dynamic power sharing. So it's just an idea. So because whatever we are doing, it's probably not. It's like probably the best in the case of you if you're assuming static powers, but the best case which we can extend it to. That's a thought. There was a thought. We did not think much deeply, but it requires more attention. But but like practically speaking, if you increase the powers of the satellites which are not contributing for the computation, then you might increase the the data in the network, and probably might improve the data-driven algorithm. Yeah.
Dear Chair, thank you very much. I think my time is almost up. It's 10 minutes.
Yeah, if you want, you can ask one more question, but it's okay like this.
Yeah, we can go to the next person.
Okay.
Thank you so much.
Thank you very much, Professor Atraya. May I now invite Professor Litvak to ask her questions.
Okay, thank you, Mr. Chairman. As a candidate, congratulations with completing your thesis. It is a very interesting piece of work, ranging from theoretical to applied. So my questions also ranging. Actually, I would like to ask you a very general question about introduction itself, and one of the first definitions that you give in the introduction, and that's definition 1.2.1 on page 4, where you define power law networks, and then you write such networks are termed scale-free because the relative distribution of vertex degrees remains consistent irrespective of the network size. So when I read this definition, I don't know exactly what you mean, because to me it sounds just like law of large numbers. This is in any random graph model. We require degree distribution to be consistent when network size increases and converge to certain probability distribution. So it does need to be a scale-free distribution per se. So I give you a second chance to redefine how can you intuitively can interpret the term that the network is scale-free.
Scale-free, okay.
Yeah, what does it mean intuitively?
Okay, So I have defined it mathematically in the equation which is 1.2.1. So that's basically probably mathematically the definition for the scale free, that the number of vertices which have a particular degree are scale like some exponent of that number of neighbors you are looking at. And because if you like look at lot of networks, this kind of property is preserved, and we see a lot of networks like that. That's why scale free network is very important.
But why are they called scale free intuitively?
Scale free because it is kind of suggesting that if you increase the scale of the network, certain things are preserved, like the number of degrees. So that's what I interpret. Probably there's some other interpretation.
So you insist on this interpretation that you give me is what is written in the thesis. Can you give an alternative interpretation?
Some other interpretation?
Yeah.
I have to think about it.
Okay, think about it. You want to think about it now, or should I go to the next question?
You can go to the next question.
Oh, okay, great. Okay, so okay, I was happy to hear that your favorite chapters was 4 and 6, because I prepared questions on those. And of course, I know a lot of questions were asked already on chapter 4, but I missed most of it, so I will now start repeating those questions. Okay, so actually first, I really like, for example, that I really like the conversion curve, especially the independence curve really was very interesting for me. But independence is maybe not the worst that can happen. I guess the worst that can happen is that two centrality measures rank the vertices in completely opposite order. Yeah. Right, the negative correlation. So how would the curve look in that case?
So it will be like a zero y equal to 0 curve for a very long time. But after some time, you have to intersect the top. You are looking at top k percent and increasing the top x percent and increasing the x. Initially, they will not intersect at all.
Yeah.
Because they are totally opposite of each other. But eventually, when you hit 1, x equal to 1, then probably you have to intersect everyone. So it will be a.
And okay, when they will start intersecting?
So probably like pigeonhole principle or something like that. Like after a point, you have to somehow, like probably after half.
Yeah.
They have to intersect.
After half, yes, of course. After half, they have to intersect, right?
They have to intersect, otherwise.
Otherwise, you don't have enough vertices. Okay, great. So that is basically that's really like lower line. Yeah. And then very interesting figures. These figures 4.1 through 4.15. And there is a little bit puzzling effect that I noticed. So at the beginning, when you compared PageRank and COTS, somewhere in the first figures, then they were like really, really similar, right? Yeah. And then suddenly, and I was not surprised because PageRank and COTS are also very similar in spirit. Mm. And at some point, suddenly 4.15, they are really different. What happened in that network? Why these two centrality measures are so different?
So it's kind of suggesting that the CCC is very much network dependent. So in a different network, you might see a different behavior. So probably, let me see. So 4.15 is the collaboration network, and it's for directed or undirected. Let me check. It's for undirected networks, and this 4.9 is for the directed network. 4.9 is for the directed network. Probably one of the difference is that both are real world networks.
So one is undirected.
One is undirected, one is directed. That might be one of the reasons, but there might be multiple reasons behind it. So this was just like simulation study. So we do not know the exact reason behind this.
Okay. You know, I agree with you that the undirectedness can be the reason. Indeed, that's very, very good answer, I think. But why? Do you think that it will be so different in undirected compared to directed?
In directed, so basic CAD centrality looks at number of paths of certain length. It's kind of a lexicographical ordering of directed paths to the network, and these are basically very strong notions, like because of the directions. So direction is like very strong, like strongly telling you that. But in undirected case, uh, you don't consider the direction. So counting the number of paths might be like, this is something which is different for the undirected and directed. It's very strong for the directed networks and very weak for
Okay.
so, but that might be one of the reasons that I can think on the spot. But
Yeah. Okay, that could be. Okay, so I also, I don't have my answer myself. It's a discussion. I promised you will have
Yeah.
discussion, so let's have discussion. Okay, so then you not only draw these curves, which is already very interesting, but you also prove some theoretical results about them. For example, you prove that under certain conditions, this curve will converge.
Right.
All right, so I believe, correct me if I'm wrong, but I believe, like, okay, you prove actually that joint convergence of PageRank and CATS centrality. Okay, so suppose you have some simple like tree-like model, like directed configuration model. Okay, then I guess it will satisfy the conditions, and the PageRank and CATS will converge jointly. Right?
Yeah.
How do you expect the curve to look like?
How do you expect for PageRank and CATS?
Yeah, so suppose you take very specifically directed configuration model, all right, and then you have the joint convergence of PageRank and CATS centrality, and the CCC converges as well, right?
Right.
So this limits in CCC, how will it look like? What do you think?
So it's very like, it's a good luck that we in these plots we have considered the directed configuration model.
So you know.
Yeah, we know how they look exactly.
Yeah. Okay.
That's a good luck. Like the question you have asked, exactly we have the plot for it.
Okay. So which one is 4.9?
For this, you do ask for PageRank and CATS, right? So it's 4.9. Yeah. Yeah. So they are quite similar for directed networks. Not very similar, but like at least better than the undirected case.
Okay, but they're not very same. Okay, interesting.
Not very same for the undirected configuration model. So the artificial network we use is the configuration model with power laws exponent 3.
So the artificial networks is on the left, right?
Artificial network is on the red. You can see red and blue a little bit.
It is on the right.
So there are 50 runs, and the red is indicating the variance of the plots.
Okay.
Yeah.
Okay. But you don't have you wouldn't be able to. I guess if I look at it, you probably wouldn't be able to derive analytical expression.
Right now, I cannot. But maybe.
Yeah, maybe because it's maybe this bumps are a little bit the finite size effect. Maybe you can.
Yeah.
Okay. Do I have more time?
Yes, you can continue.
Okay, that's great. Okay, so now also another very interesting thing that you consider in thesis, and something I also worked on before, is locality of almost local centrality measures like PageRank and CATS. So PageRank and CATS have this in common, that they both have this damping factor, and at least this is what makes PageRank local. Do you think that any centrality measures that has this type of damping factor will be local?
Yeah, so I have devised a method how you can find some centrality measures like that, and I mentioned it in one of the remarks, I think. I'll just find that out and just mention that. So in section 4.6, where I discuss about locality and of centrality measures, so in the 2 points at the end, so at page 112, 2 points which I state. So if you have a strictly local approximation which is monotonic in n, that and the expectation of the error basically that goes to 0, then you can directly say. So this is basically the things which we need for the convergence of CATS. Then you can say that this centrality measure.
Okay, but will harmonic centrality satisfy that?
So for harmonic and closeness centrality measures, we have the first step, like you have a monotonically increasing approximation, so which ensures the first step. But the second step is a little bit complicated because it's highly non-local centrality measure. So getting that into hand, you might need some conditions. So conditionally on conditioned on the second equation, the harmonic and closeness centrality will converge, but it will not. It is not like universally like CATS and PageRank are always satisfies these conditions. But for harmonic and closeness, this might be true. So for all networks, for some networks that might be true.
But don't you think so? Harmonic has inverse distance, so it's 1/r basically for the vertices at distance r. And don't you think that it is important that there is some kind of integrability? Like 1/r is not an integrable function, so maybe the second condition will not be satisfied. Do you think there is a relation between the second condition and say integrability of that function of R that centrality includes?
Probably, because obviously expectation is an integration. It's a measure, integration with respect to a measure. So and the condition involves expectation. So, and yeah, as you are clear, probably that might be one of the reasons. But you are talking about a difference, and that difference might become very small for certain networks, but not for all networks. Obviously, you cannot show, like for cats and PageRank, you were able to show for any arbitrary network this will hold.
Okay.
Yeah.
Okay, interesting. All right. Am I with time? That's it?
Now, I might like to give the floor to Professor van der Hofstad. So
Okay,
if it's
good.
okay with you.
Okay,
So thank you very much
for your answers.
Professor Litvak. Professor van der Hofstad.
Thank you, Mr. Chairman. Geachte lighter. Sort of along the lines of the question of Professor Atreya, he asked about the most impactful result. I'm going to ask you about which result you're the most proud.
Proud.
Yes. You've written an entire book. There must be parts that you're more proud of than other parts.
I'm proud about the whole book. Yeah. So.
Okay.
Yeah.
The completion of it.
Completion of the book. Yeah. So.
But if you were to name one result, what would it be?
It's like the synergy. Like you cannot choose between your fingers, like your children. It's like that. Probably. I don't know.
Okay.
Like, probably that's a good.
That's a good answer.
Yeah.
But I'm going to be teasing you a little bit more in a slightly different direction, namely, what is your favorite centrality measure?
Favorite centrality.
And maybe you can answer why.
So I actually mentioned it in my slides, not like exactly the same way. Probably PageRank, because in a certain sense it revolutionized the 21st century, and suddenly Google and stuff, like things happened, and I'm here because of internet, because I would have never known about TU Eindhoven if I was internet was not there.
That's a very personal and clear answer.
Internet is very important. So and my
Now suppose that Brin and Page would not have invented PageRank.
Yeah.
It's not entirely clear whether the page in PageRank actually stands for the page in the person page.
Yeah.
But suppose they would have invented Katz's centrality instead.
Yeah.
Would the world have looked rather different? In a certain sense, that's a comparison between centrality measures.
Yeah.
But it's qualitative.
Qualitative, yeah. So probably I think so, because but given that my curves which I have plotted, it shows for directed networks they are not very much far apart. For undirected, they are very way apart. So probably for the World Wide Web, which is a directed network, it might have been not that different, but probably significantly different. Probably I would have not been in Eindhoven. I don't know.
You would have landed somewhere else.
Somewhere else.
Well, that would have been a significant change to my world in any case.
Okay.
Right. So I'm trying to build a bridge between some of the chapters that you've written of your booklet. So on the one hand, you study these vertex removal processes based on centrality measures. So you remove the most highly ranked vertices, and then you look at the size of the giant component and the number of connected components and these kind of things. You could think of that as being a bit of a cascade. You study cascades in chapter 6.
Right.
But the cascades are formulated a bit differently.
Right.
Can you build a bridge between these two different things, or are they completely different?
So it depends on the centrality measure in hand. So for example, for the degree centrality, the most commonly known cascade, the K-core, which I define in my chapter 6.
Yeah.
First example which I give. So that is on basis of a centrality measure itself.
Yes.
So for
indeed.
centrality measures, some certain centrality measures which might make it monotonically increasing property, you may use it, but like not for all.
Thank you, Mrs. Beadle. I would like to ask the candidate to return to his seat. The committee will now retreat and discuss the quality of the thesis and the defense to determine if a degree of doctorate can be approved. I hereby adjourn the public defense session.